Okay, moving on to the next part. We're going to look at how cardiac output is calculated, and then we'll go from that into how cardiac output is regulated. Cardiac output is defined as the volume of blood pumped out by the left ventricle in 1 minute. Now keep in mind that the right ventricle is going to pump pretty much the same amount. They're going to reach equilibrium where they're each pumping pretty much the same amount from one beat to the next. We're going to calculate cardiac output by multiplying heart rate times stroke volume. Now we have to figure out what stroke volume is. You can't really do this unless you're doing it experimentally. Anybody can measure heart rate, right? You just put your hand over your heart and count the beats per minute. The factors that affect heart rate include autonomic innervation and hormones. Sympathetic, of course, is going to speed up the heart. Parasympathetic is going to slow it down. You remember that the sympathetic nervous system also stimulates the adrenal medulla to secrete epinephrine, so that's a hormone that can speed up the heart, and there are others as well. Factors that affect stroke volume are going to be the end-diastolic volume and the end-systolic volume. Now, I want you to think about this. We know that the amount ejected, the stroke volume, has to be the difference between how much you started with and how much you ended with, the EDV minus the ESV. But there are different ways of affecting that. For example, the sympathetic nervous system can make the heart contract more strongly, and that's going to squeeze more blood out, which is going to make the ESV lower, which is going to increase the stroke volume. On the other hand, though, when you're sympathetically stimulated, you constrict your veins. And when you constrict your veins, that sends more blood back to the heart so that at any moment the end-diastolic volume can be higher than resting values. So there are different ways of regulating cardiac output. Okay, so stroke volume we know is in diastolic volume minus in systolic volume. Another aspect of measuring that is called the ejection fraction. This allows for how big your heart is or how much blood was in your heart. So the ejection fraction is the percentage of the end diastolic volume ejected during contraction. So let's just say your end diastolic volume was 130 milliliters and your end systolic volume was 65. Well, 130 minus 65 equals 65. So that means your stroke volume, 65 milliliters, is exactly half of your end diastolic volume, and that's 50%. So that's the way it's calculated. Figure out the stroke volume, divide it by the end diastolic volume, convert it to a percentage, and that tells you what an ejection fraction is. A normal ejection fraction is going to be, maybe not exactly 50%, but it's not going to be 100%. It's usually somewhere around half or so, maybe 40% to 60%. Okay, so in this diagram, what you're looking at is pressure changes and the effects on the valves. Look at the little valve at the bottom of the syringe. And here we have our end diastolic volume. Notice all our valves are closed. And here we're pumping it out. So that's the amount that leaves is our stroke volume. The amount that's left behind is the end systolic volume. Okay, so factors that can affect cardiac output are things that affect either heart rate or stroke volume. We're going to look first at the things that affect heart rate. Autonomic activity and hormones are primary. So we need to know about the nerves that supply the heart. We have sympathetic nerves and we have parasympathetic nerves. And these nerves are connected to centers in the brain. And the centers in the brain are called the cardiac centers. One speeds up the heart and one slows down the heart. And these cardiac centers sit right next to each other in the medulla oblongata. Obviously, cardioacceleratory is going to control sympathetic neurons to increase it. Cardioinhibitory is going to send parasympathetic impulses to slow it down. Now, you also need to remember that the vagus nerves are parasympathetic. The vagus nerves are cranial nerve 10. There's one on the right, one on the left. The vagus nerve on the right goes to the sinoatrial node. The vagus nerve on the left goes to the atrioventricular node. So that just slows the heart down. The cardiac plexus is a network. A plexus is a network of nerves, and the cardiac plexus arises from sympathetic nerves in the sympathetic chain and can mix with branches off the vagus nerve to supply the heart. Okay, our reflexes, our cardiac reflexes, they're actually two different kinds. We have baroreceptors and chemoreceptors. So we have baroreceptor reflexes and chemoreceptor reflexes. These are not hard to keep straight. Just start, thinking about them separately. Baro refers to pressure, and obviously chemo refers to chemicals. So baroreceptors are monitoring how much pressure the heart is under, how much pressure the blood is under. And chemoreceptors are monitoring, do you have enough oxygen and is the carbon dioxide being removed? So I'm sure you can imagine that if you had too much carbon dioxide in your blood, that you need to get your blood flowing to the lungs faster to get rid of that carbon dioxide, and that would stimulate an increase in heart rate. Whereas if the blood pressure is too high, your baroreceptors are going to recognize that the pressure is too high, and it's going to inhibit the heart and stimulate parasympathetic. Now, we have this idea called tone, and tone is just a chronic, continual, low-level stimulation. So autonomic tone occurs when signals are being sent pretty much all the time unless you tell them not to. So dual innervation, I know you remember from ANP1, means both sympathetic and parasympathetic can send opposite signals. You probably don't remember this. If you do, that's great for you, but I'm going to remind you. Acetylcholine is a parasympathetic neurotransmitter. Norepinephrine is a sympathetic neurotransmitter. So if you put acetylcholine on the heart from your vagus nerves, it's going to slow it down. And if you have norepinephrine being delivered by your sympathetic cardiac nerves, that's going to speed up the heart. Okay? So we have these baroreceptors that are located, actually some of them right on the aorta. Some are monitoring blood pressure to the brain up at the carotids, right at your jawline. And then we have chemoreceptors, again, right along the aorta. And they're just constantly monitoring, and they're going to send signals up to the cardioacceleratory and cardioinhibitory centers to just constantly adjust cardiac activity. So here on this picture, you can see on the left the sympathetic, and on the right the parasympathetic. So you remember this from ANP1, that sympathetic nerves arise from the thoracic region of the spinal cord. They have to go out through the sympathetic chain ganglia. So following from the cardioacceleratory center at the top, going down through from the medulla to the spinal cord, coming off at the, about T1 to T4, and then going up to the cervical ganglia, along with superior ganglia, and then going out through the cardiac nerves, and those nerves are going to the sinoatrial node and the AV node to speed it up, but they're also going to send impulses out to the ventricular muscle to make it contract more strongly. On the right, on the parasympathetic side, we have the cardioinhibitory center up in the medulla. It sends signals to the vagal nucleus, which is also in the medulla. It goes out the vagus nerve. It just shows it on one side. It's actually happening on both the right and the left. The right vagus nerve slows down the SA node. The left vagus nerve slows down the AV node. And if there are branches that are going to the cardiac muscle, we're not really sure what those are doing. All we know that parasympathetic can do is slow it down. Okay, so the SA node, remember, reaches threshold faster than the cardiac contractile cells or the AV node or any other cells in the heart, but the effect of acetylcholine from parasympathetic is to slow it down, and the effect of norepinephrine from the sympathetic is to speed it up, which means it's going to reach threshold sooner if you speed it up, and it's going to take longer to reach threshold if you slow it down. So here you see the action potential of the pacemaker cells. This is normal. Now remember, at normal, we actually are sending signals, parasympathetic signals through the vagus nerves, through autonomic tone. This is called vagal tone. If you cut the vagus nerve on the right, your heart rate will instantly jump to about 100 beats per minute. So what this calls normal is really just with vagal tone, with the autonomic parasympathetic fibers constantly slowing it down. But acetylcholine is going to make it go down, and norepinephrine is going to make it go up by changing. Look on this slide, you're seeing the effect of parasympathetic stimulation. It hyperpolarizes the cells. It makes them give out more potassium, which makes them farther from threshold, which makes them take longer to get to threshold. So the effect of acetylcholine is actually to cause extra potassium to leave the cells. And in sympathetic stimulation, then it doesn't repolarize as much. Norepinephrine shortens repolarization. It closes those potassium channels sooner so that the cells don't ever get that far from threshold to begin with, so that they can race to the next heartbeat more quickly. All right, we'll look at some reflexes. The Bainbridge reflex, that's an old term. It's very often called the right atrial reflex, and it's a response to increase in venous return. Venous return just means the amount of blood coming back to the heart through the veins. And, of course, the right side is the side that's getting that blood from the systemic veins. So if you are active, or even if you just think about becoming active, your veins tend to constrict. Your inferior and superior vena cava are going to deliver more blood back to the right atrium. And that's going to make the right atrium stretch a little bit as more blood comes back in. And that stretch stimulates receptors in the right atrial wall, which stimulates the sympathetic nervous system and says, hurry up, because there's extra blood coming. It also actually triggers a response that just makes the muscle contract more strongly just from the stretching alone. And of course, all that sympathetic stimulation also causes the release of epinephrine and norepinephrine by the adrenal medulla. And additionally, this is an interesting effect, but it's not part of the reflex. Your thyroid hormones stimulate the heart. Now, this makes sense because your thyroid hormones are stimulating your metabolism. But if you have a patient who's on a thyroid supplement, they aren't making enough thyroid hormones, so they take a thyroid pill. If you give them too much thyroid hormone, it can cause tachycardia. And, of course, that can get serious enough to make them not pump enough blood, and they get faint and they pass out. So thyroid hormone also stimulates the heart, makes it speed up. All right, things that affect stroke volume include anything that raises the EDV by either slowing down the filling time or increasing venous return, or can decrease the ESV by increasing the strength of contraction. All right, preload is simply a measure of how much blood did you just dump into the ventricles. The more blood you dump in, the more the ventricles stretch, and the more they're going to be likely to, just as a negative feedback, to pump it back out. So the higher the preload, the stronger the contraction will be. EDV at rest is low, and it rises with exercise because venous return increases, the myocardium stretches more, and you stimulate a stronger stroke. The Frank-Starling principle is not an autonomic response or a hormonal response. It's just a natural intrinsic response of the muscle itself. The more you stretch the heart, the stronger it contracts. It's that simple. Okay, so 3 things that affect in systolic volume: preload, how much blood came in; contractile force; and then the afterload. And the afterload is how much are you pushing against in the arteries to push the semilunar valves open. So if your blood pressure is too high, then the heart is having to push against a higher blood pressure, and that can reduce the ability to pump blood out, which is going to prevent the blood from leaving, which is going to lower stroke volume and an increase in systolic volume. So the problem with afterload is in people with hypertension. The higher the blood pressure, the more force it takes to push the blood out of the heart, the less blood actually leaves, the lower the stroke volume. And you can actually get blood, we call it congestive heart failure. The heart becomes too weak to pump the blood because it's pumping against such a high pressure, and that then just kind of domino effects into the weaker the heart, the less it pumps, the weaker it gets. And blood can actually back up into the lungs, and you get pulmonary congestion. And then that affects the ability to get oxygen into the blood and can cause some very serious long-term problems. Okay, so we know that sympathetic stimulation increases heart rate, but it also stimulates stronger contraction. Norepinephrine and from the cardiac nerves, epinephrine from the adrenal medulla can increase the force of contraction of the ventricles. That increases the stroke volume, it increases the ejection fraction, and lowers the ESV to the point where you might only have 20 milliliters or so of blood left in the ventricles instead of the usual 50 to 60 milliliters of blood. The parasympathetic system, as far as we know, has a dominant effect on slowing the heart down. Remember, vagal tone at rest just continually keeps the brakes on your normal heart rate. Your book says it reduces force of cardiac contractions. I haven't seen that routinely listed somewhere else or anywhere else about the parasympathetic stimulation. Definitely some hormones affect, epinephrine and norepinephrine. We saw thyroid hormone. And hormones can be mimicked by drugs. So there are a lot of drugs that can affect the heart the same way the hormones do, or the opposite by blocking them. So we have alpha and beta receptors on the heart for epinephrine to have its activity. So we can have beta blockers, which can block calcium channels and decrease the heart rate or decrease the force of contraction. So you have this very complicated figure in the book. What I'm going to ask you to do is just go through and follow it. See if it all makes sense. See if you can put it all together and pay attention to what increases and what decreases, and try to, in your heads, make sense of what would happen if I need my blood pressure to go up versus what would happen if I need my blood pressure to go down, because cardiac output is directly related to blood pressure, and if the blood pressure is too low, the blood won't flow, and if the blood doesn't flow, then you have a cardiovascular situation where you have basically no blood flow, circulatory shock. Okay, so in summary, to control cardiac output, you control the heart rate or the stroke volume or both. You can control it through the autonomic nervous system, sympathetic and parasympathetic. You can control it through hormones, and you can control it through those intrinsic factors such as venous return and stretch receptors. Okay, so factors that affect heart rate are summarized here. Factors that affect stroke volume are on the left. Remember that cardiac output is heart rate times stroke volume. So try to put all this together, make sure it makes sense to you, and then go through the reviews that I've listed and make sure that those reviews make sense. All right, cardiac reserve is simply, what can I do when I'm exercising? How much more blood can I get to flow? Cardiac output, if you measure it numerically, is stroke volume times heart rate. If a normal stroke volume is about 70 milliliters and a normal heart rate is about 75 beats per minute, then that works out to about 5 liters per minute. Normal cardiac output is about 5 liters per minute. If you're a well-trained athlete, then at your peak performance, you might be moving 35 milliliters per minute. Well, that's 7 times more blood per minute, and that's a measure of your cardiac reserve. The fitter you are, the higher your cardiac reserve will be. All right, so we've covered regulation of the cardiovascular, the cardiac centers. We've talked a little bit about, we haven't really talked about activity patterns, rest versus activity a little bit. And then circulatory emergencies, that's going to be like circulatory shock, and that will make more sense, I think, a little bit later. So read it, review it, do your mastering assignments, read the reviews, answer the review questions, and then take your practice quiz.